Hello students, uh, today I will tell you the Neet 2019 question paper series H1. This is the question paper when the Neet exam 2019 was held once more. The questions language or the some of the questions were very much doubtful in the first uh, exam held by the government. So because of that it was decided that once more there should be the exam of Neet 2019. So second time it was held. So many the students who were not satisfied with the first one, they appeared in the second chance, and many of the students who were not qualifying in the first attempt qualified in the second attempt. They qualified in the second attempt. So I am taking the series H1. And I have told you that whatever series are there, A, B, C, D or P, Q, R, S, like this, the questions are the same in all, but sequence of the questions is changed so that no one could cheat with the neighboring student. So now I am taking the Neet 2019 solution H1. The first question of this series the first question is, and today I will take the less questions because language are the lengthy, so to write them and then to explain it takes more time. So now today I will take 1 to 7. Question number 1 to 7. Now your first question is the radius of first permitted Bohr orbit. The radius of first permitted Bohr orbit for electron in hydrogen atom equals to equals to 0.51 angstrom, and its ground state energy ground state energy equals to minus 13.6 electron volt. If electron in hydrogen in hydrogen atom is replaced by mu1, by mu1. Mu minus 1. Mu1 having charge same, having charge same as electron, and mass mass 207 ME, the mass of electron. The first orbit and ground state energy will be the first orbit and ground state energy will be, now your first is 2.56 into 10 raised to power minus 13 meter, and this is your minus 13.6 electron volt, and second is 0.53 into 10 raised to the power minus 13 meter, and energy is minus 3.6 electron volt. Third is 25.6 into 10 raised to the power minus 13 meter, and energy is minus 2.8 electron volt. And fourth is 2.56 into 10 raised to the power minus 13 meter, and then minus 2.8 electron volt. These are the options. Now the solution. Here clearly given the first permitted Bohr orbit, so you must know the formula of the radius of the orbits and also the formula for the energy of the electron. And we know that radius r equal to n square h square upon 4 pi square m k square z e to the power 4 k z e to the k z e square k z e square. So now clearly this r is proportional to 1 upon m. Only m is changing, remaining the charge is the same. So there is no change on this the charge E. So now you can have that RH upon R mu is equal to m mu upon me. So this is equal to m mu. M mu is 4 times 207 of me upon me. Now this will cancel. So this is equal to 207. You have to find the R mu. Therefore, R mu equal to, this is now your RH, 207 into RH. This is now 207 and RH is given 0.51. 0.51 angstrom. This is the given the value, and now product of this one is coming out to be This is now 2815.2 angstrom. No, 2.56. This is 2.56 into 10 raised to the power minus 13 meter. So this 2.56 10 raised to the power minus 13. This is now coming here. 2.56 10 to the minus 13. Now we have to confirm about the energy. Energy E equal to 2 pi square m k square z square e to the power 4 upon, this is now your n square h square. So now we know that this E is proportional to m. So E h upon E mu equal to, this is your mh upon m mu. And now again we are having to this one that eh upon E mu equal to eh, this is now your mh upon m mu is equal to 207 into E mu. mh, the mass of the electron. Here is the mass of the electron, so this is now me. Me, and this will cancel. So you can have that E mu equal to 207. This is not like this. R mu equal to RH upon 207. RH upon 207. RH 0.51 upon 207 angstrom. So it will come out to be 2.56 into 10 raised to the power minus 13 angstrom. So much. And this is now E mu equal to 207 into EH. And 207 energy of the electron EE, and this is now your 207 into minus 13.6 electron volt. So it will come out to be approximate minus 281.2 electron volt. So now you can write to this one minus 2.8. Wait 1, 2, 3 places. So this is now will be converted into kilo. This is now kilo electron volt. 2.8. This is also in kilo electron volt. Kilo electron. So our right answer is fourth one. So this is the first question. So this is the direct application of the formula of electron in the hydrogen atom, the radius of the orbit and the energy of the electron. And now second question. Now the reading of an ideal voltmeter. The reading of an ideal voltmeter, ideal voltmeter in circuit. Shown is, now first option is, now first we draw the diagram. This is now voltmeter. This is your 20 ohm. This is 30 ohm. This is your 30 ohm. This is 20 ohm. And this is a battery of 2 volt. 2 volt. Now your first option is 0.4 volt. Second is 0.6 volt, and third is 0 volt, and fourth is 0.5 volt. So this being just like a Wheatstone bridge, there will be no current in this voltmeter because there will be it has the infinite resistance. So even if you can see that if we do not consider this voltmeter, then these two resistances are in parallel. This is also in parallel. So now we can have the solution of this is solution. The resistance of ideal voltmeter is equal to infinity. So now we take this as to this is now 20 ohm, this is 30 ohm, this is 30 ohm, this is your 20 ohm, this is now your voltmeter V, this is a battery, this is 2 volt. So let the current here is I, and that it is divided here in 2 arms as I1 and I2. So leaving this voltmeter, we can have this is now 50, this is now 50. So equivalent resistance, resistance 1 upon R equal to 1 upon 50 plus 1 upon 50. So this is equal to 2 upon 50, or R equal to this is 1 upon R equal to, this is in series, 50 is in series, then both are in parallel. Parallel 1 upon R equal to this, so much 50 upon 2, so this is now 25 ohm. So current I equal to V upon R. V is equal to 2 upon 25, so much ampere. So I1 and I2 will be divided equally, because this is also 50, this is also 50. So I1 is equal to 1 upon 25 ampere, and I2 equal to also this 1 upon 25 ampere. Now let this is A, P, and this is now Q. Now we find the potential difference in AP. So we find this VA minus VP equal to I1 into 20. So this is equal to I1 is 1 upon 25 into 20, so this is now 4 upon 5. This is what this VA minus VP. VA minus VP is equal to 4 upon 5, or VA minus VP equal to 0.8. This is now number 1. Then this AQ. So we will find this VA minus VQ is equal to I2 into 30. Now this we can have, now from this VA minus VQ equal to I2 is equal to 1.5, this is now your 30. So this is your 6 upon 5, so this is 1.2. This is VA minus VQ. This is now number 2, equation number 2. So now you find VP minus VQ. Therefore, VP minus VQ. So VP this will be negative, this will be now positive as it is. So 1.2 minus 0.8, so this is equal to 0.4 volt. This is the reading of the voltmeter. Reading of voltmeter equal to 0.4 volt. So now right option is 4th. So first what we have to consider here is to keep in mind is that voltmeter is ideal. So resistance will be infinity. And if suppose it would not be infinity, then this is the unbalanced Wheatstone bridge. So we cannot find the potential difference like this. So this is what to be keep in mind. Then there will be no current in this one. So just you find that is 20 and 30 are in series, 30 and 20 are in series, then they are in parallel. So find the equivalent resistance by this formula, and then the current in this circuit. And let this current is I. I is equal to so much. When I is equal to so much, then you can find this I1 and I2, because the resistance in both the arms are equal. So current will be divided equally. It means that I1 equal to 1 upon 25, and this is also 1 upon 25 ampere. Now then find VA minus VP. VA minus VP. So this is I1 into 20. Resistance is 20. Now this is so much. So 4 upon 5. This is so much. 0.8. And then VA minus VQ. VA minus VQ. This is 1 upon 25 into 30. This is now 30. 6 upon 5 is 1.2. Now you find VP minus VQ. VP minus VQ. So VP, we have to take it negative, and this will be now positive 1. So this is now 1.2 minus 0.8, so 0.4 volt. So voltmeter reading will be 0.4. So our answer must be what? The first one. This is not right answer. Now the third question. A meter is shown in balance position. Balance position with P upon Q equal to L1 upon L2. If we now interchange, the position of galvanometer and cell. Will the bridge work? If it is in the will the bridge work? If yes, what will be the balance condition? What will be the balance condition? Now the given in the figure is, this is the cell, this is like this, then we have a this is now galvanometer connected to this. This is your P, this is Q, this is L1 and this is L2. This is your plus minus, and this is the given, and the options are, the first option is yes, P upon Q equal to L1 upon L2. Second, yes, P upon Q equal to, this is L2 minus L1 upon L2 plus L1. And third choice is no null point. And fourth option is yes, P upon Q equal to L2 upon L1. Now solution. What is given in question? This is given the condition. The bridge in balance, so P upon Q equal to R upon S. We have the formula P upon Q equal to R upon S. This is like this. This is P, Q, R and S. This R is given to be L1 and this is given to be L2. So P upon Q equal to L1 upon L2, because we know the resistance depends upon the length of the wire. This is the given condition here according to this one. Now what is said in the question, that the position of galvanometer and ammeter are interchanged. So just you interchange. This is now battery and this is now galvanometer. This is P, this is Q, this is R, this is resistances are as such. There is no change in this one. So what we need for the balance of this bridge, that resistances must hold this condition P upon Q equal to R upon S. Because the resistances are not being changed, it means that this condition will hold. Either we interchange this voltmeter and ammeter or not. So this will the condition, and the bridge will work. There we will get the energy, we will get the null points. So remember that in case of meter bridge, the balance position depends upon the value of the resistances. If resistances are kept in the same situation, then balance condition will not change, whatever be the position of the voltmeter of this cell and the galvanometer. So this will hold and we will get the balance position. So the what we said that will work, then this is now yes, and this P upon Q equal to L1 upon L2. So in place of R upon S, this is what? L1. This is what? L2. So we are not changing this R upon R and S, so no change in this position. So this bridge will work and the conditions will be held and we will get the null point. So our right answer is, where to find this? No, first, yes, P upon Q equal to L1 upon L2. So our answer is now first one. End of question number 4. Now question number 4. Now fourth question is the relation amongst the three elements. The relations amongst the three elements of Earth's magnetic field. Earth's magnetic field, namely horizontal component H, vertical component V, and V and dip delta. Dip delta R. Now option is, first is your V. Now here is one more given, this BE equal to total magnetic field. Total magnetic field. So first option is B equal to BE and H equal to BE 10 delta. Second option is V equal to BE VH 10 delta and H equal to B. And now third option is V equal to VE sin delta and H equal to BE cos delta. And now fourth option, V equal to BE cos delta and B and this H equal to BE sin delta. These are the four options. Now solution to this question. Now we know about the Earth's magnetic field and the components, the vertical component, horizontal component, and the angle of dip. These are called the elements of the Earth's magnetic field. So this is like this. Let me draw it here. This is now DE, total magnetic field. This is the angle of dip. This is the horizontal component H. This is vertical component V. So now you can have that this is the right angle triangle. So from this you can find that H cos delta is equal to base upon hypotenuse H upon VE, or H equal to VE cos delta, and sin delta equal to V upon VE. So from V equal to VE sin delta. So H equal to so much and V equal to so much. This must be the right option. So here we have the right option is third. V equal to VE sin delta and H equal to VE cos delta. So one answer is third. Though this is told to the students in the chapter, and some of them know that how to find what is the relation between them, so you can do it directly. But if suppose some student have forgotten and don't know, he has forgotten that what is the relation between these components, then just to draw the diagram, and you must know that this is the vertical, this is the total magnetic field, this is the horizontal component, this is the vertical component, this is the dip, and then find from the right angle triangle that this H and the value of V. So that you will find the right option. And now question number 5. NaU2. NaU2 as shown in figure. As shown in figure, water and oil. Water and oil in the left side and right side. Side and right side respectively. The height from the bottom of the height from bottom for water and oil columns. For water and oil columns. Oil columns are 15 centimeter and 20 centimeter. Respectively. The density of oil is the density of oil. Oil is. Now this is given that take raw water. Raw water equal to 1000 kilogram per meter cube. This is given. The figure is given here. First I will draw the figure. This is and then we have this up to this one. This is your 15 centimeter. So much. This is 20 centimeter. So much. Here this is the water and this is the oil. This is given. And now your options are, first is 1333 kilogram meter minus cube, and third is 12 kg per meter cube, and your third option is 750 kg per meter cube, and fourth is 1000 kg per meter cube. This is the question. When we see the language and so much lengthy one that some of the students are frightened that how to read this so much language and then to understand and then to solve this question. So many of the students leave this such questions. But this is not to leave. If you understand to the language of this question, then you can find the solution easily. You see that both the ends of the U2 are open. It means that there is working the atmospheric pressure, and also there is pressure of this water and oil. So two pressures are there. First is the oil and water pressure, and then the atmospheric pressure. So now solution how to do? Atmospheric pressure. Let this is now your P naught. So pressure on this and pressure on this must be equal because this is now in equilibrium. They are not moving at all. So what we have this P plus rho W H W into G equal to P naught plus rho oil into H oil into G. H rho G, HdG, the direct formula is HdG. The pressure because of this liquid HdG, because of this HdG, now heights are given the different and the densities are different. G is the same for both sides. So this P naught and P naught will cancel. Rho W, this is given to you 1000. HW is given to 15 centimeter. This is now G. Rho oil, this is you have to find H20 and this is now given G. So G and G will cancel. And what we have? This 20, 25 the this so much. And then rho oil. This is now your 50 into 15. 15 7 the 750. So much kilogram per meter cube. Now you can see that this is the very small solution, but this language is the lengthy one. So sometimes the question solution is not too large, but the language is very hard, and this is given to so much long that some of the students do not like to solve such questions. They leave it. So you have to go through it. And always remember, when the condition is like this, both the ends are open and the liquids are in equilibrium, then just we apply the pressure on this side is equal to the pressure on this side. So this will be equal, and then find the rho oil. So our right answer is third, 750. Kilogram per meter cube. This is now question 5th. Now I will take the question number 6th. Sixth is given a deep rectangular pond. A deep rectangular pond of surface area A. Surface area A containing water density rho. Density equal to rho. Specific heat capacity S. Specific heat capacity equal to S is located in a region. Is located in a region where outside temperature air temperature is at steady value of minus 26 degrees Celsius. The thickness of frozen ice layer frozen ice layer at this point at certain instant is X. Taking thermal conductivity of ice. Taking thermal conductivity of ice as K and latent heat of fusion as L. The rate of increase of the thickness of ice layer at this instant would be given by. Now your options are, first is 26K upon rho x into L plus 4s, and second is 26K divided by rho x into L minus 4s, and third is 26K oblique rho x square into L, and the fourth option is 26K upon rho X and L. This is now the question. What is given here? A deep rectangular pond of surface area A contains water density rho, specific heat capacity equal to S, located in the region where outside air temperature is at a steady value of minus 26 degrees Celsius. Minus 26 degrees. From here you have to understand that the water freezes at 0 degrees centigrade or below the 4 degrees centigrade. So what happens that when the temperature is given to be minus 26 degrees Celsius, it means that only there will be the heat of fusion. So that on this one, the thickness of the frozen ice layer is in this point is certain distance is x. Taking thermal conductivity as K and the heat of the fusion is equal to L, the rate of increase of the thickness of the layer at this instant would be given by so and so. So what we have done? Solution, this is the layer, it has the area A, this is ice layer, ice layer, and it has the distance, this suppose so much, and at any time this is given to be now x, and this is the increase in its depth, its thickness. Let this is now your delta x, this is now delta x. So what the energy will be taken from this the outside air. So we will write down this Q equal to, also given here that one more point to be noted here, that we are given the thermal conductivity. Thermal conductivity, it means that you have to apply the formula of thermal conductivity. So Q is equal to Ka delta theta upon delta theta upon x into time. The time is t. T is the time. T is the time. And Q is equal to ml. Latent heat of fusion is equal to Ka delta theta upon x into t. Now we have to put. Now when the ice, this will freeze, the water will freeze, then its mass, what do you say, that there is a change in mass because volume will increase. So there will be change in the mass of the ice. As more and more water freezes, the more and more mass will be of the ice. So this mass, so how will you find this mass? Where mass m equal to the density of this is given to be now rho density into the volume. How to find the volume? And you are given the area A and the thickness delta x. So area into thickness, that will be the volume. Area A into thickness delta x, that we have considered. This is the mass. So we will put down the value of this here. Therefore, this is rho A delta x into L equal to K A into temperature is, how to calculate this temperature? This is given to now is minus 26 degrees Celsius. So the water is at 0 degree centigrade. So this is now your 0 minus 26. This is now your temperature delta theta upon x, and then multiplied by T, the thickness. So now here this A and A will cancel. You have to find the rate, the delta x upon T. Therefore, delta x upon T is equal to, this is minus plus, so this is now 26K upon what we have, this x, T coming out to be rho and L. So this is rho, L and x. This will be the rate of increase or the thickness of the ice. Rate of increase of thickness of ice is equal to delta x upon T, and this is now 26K upon rho L into x. So just to match your answer, this will be so much. The fourth, 26K rho x into L. So our choice is now fourth. So if you read this, you can, if you see the language, and this is long one. And again I have told you that when the question is given long, then try to understand it. What is given. And one point to be remembered here, this that here given the thermal conductivity. So you apply the formula of thermal conductivity. And this Q equal to Ms, there will be no change in Ms delta theta, the no specific heat. And this, in case of ice, we are given this L. And now you put these values. M you find like this: the density of the water, the area of the pond into the thickness of the ice. So this will give you the mass, and then find of this one, and then this will, and this temperature will be 0 minus 26K. Now question number 7. An LED is constructed. An LED is constructed from a PN junction diode. From a PN junction diode using gallium arsenic phosphorus. The energy gap is is 1.9 electron volt. The wavelength of the light emitted, the wavelength of light emitted will be equal to now option is first 654 into 10 raised to the power minus 11 meter. Second is 10.4 into 10 raised to the power minus 26 meter. And third is use 654 nanometer, and fourth is 654 angstrom. This you have to find. Now here the solution is the light will be emitted when the energy of the photon is equal to the energy gap or more than this. So now E equal to h nu and hc upon lambda. hc upon lambda. You have to find the lambda. Therefore, lambda equal to hc upon E. Now E is given in electron volt. So what we do? You put the value of h and c and then this one. So there is a formula directly to be used here. 12,400 upon E in electron volt. So much answer. And now you can put the value 12,400 upon, this is only 1.9, so much angstrom. Then if you divide, you will get it to be 652.6. So much angstrom you will get it. No. Point. This is your 3. And now you can see that the answer is here is the 3 digits 654. This is now 654. 653. So if we write down it, this is now 656.3 into 10 raised to the power minus 10. Then suppose we bring the point here, then 652. We have to 0.6 into 10 raised to the power minus 9. And if we write down the answer in 3 digits, these 3 digits, then you will find that we have to leave this 6, so we can make it to be 653 into, this is so much nanometer. This is equivalent to this one, 654. So our answer is third. This is not right answer. So this is what I have told you about the Neet 2019, which was held second time, and the question number 1 to 7, and I have solved them. Also I have explained this too, how to solve the question. You remember that my method of solving the question may be different from the others also, because whatever I think that nothing should be given directly, because when something is direct, then we forget. So we make the selection of wrong choice. So remember that in physics always we take on the ground state. So you have to apply the formula, you have to calculate, and you have to understand. And if suppose you have been forgotten some formula, then you derive it, and you will get not in more than in a minute. If you have good practice and you have done so many questions belonging to the same formula. So you all like, share and subscribe the video. Thank you very much.